This is Calculus 2 video lecture number 29 on calculus with parametric curves. So if you'll recall, we recently started studying parametric curves where we have typically two functions, x, which is a function of t, and y, which is a function of t, where t is our parameter. And remember, as the values of t vary, then so do x and y, and they trace out a curve in the plane, in the xy plane for now. So to continue this study, now we're going to look at how we can find tangents to these parametric curves. And as we know in our studies of calculus, if we're going to find a tangent line to a curve, we first need to find the slope of that tangent line. And we do that by finding the derivative, or dy dx. So what is dy dx equal to on a parametric curve? How do we find it? The formula is actually pretty straightforward. In fact, you could probably guess what it's going to be if I didn't tell you. It's equal to dy dt over dx dt. Okay, that's our starting point. Also, we might be interested in studying the concavity of these parametric curves, in which case I'm going to need the second derivative with respect to x. So we have to be a little more careful here. If I want d squared y over dx squared, so the second derivative with respect to x, let's remember what this represents. You take dy dx, and then we differentiate it again with respect to x, right? That's how we find the second derivative. And now be careful here, because I want you to look up at our definition or our formula for dy dx. So if I differentiate y with respect to x, I have dy dt in the numerator over dx dt. Similarly, if I'm going to differentiate dy dx with respect to x, look what happens. I have the derivative with respect to t of dy dx, the first derivative. Let me color code everything for you. And then I divide this by dx dt. Okay, so this is the formula when we're finding the second derivative with respect to x. Just be careful, because a very common error I see a lot of students make, and I don't want you to fall for it, okay? They think the second derivative with respect to x is found by just differentiating each of the parametric equations independently with respect to t twice and then taking their ratio, and that is not the way to go about it, okay? No, 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 I'm going to put a big X. Don't do this, don't do this, okay? So we'll practice an example so you can see exactly how the process works. But just keep in mind when you get that second derivative, pay close attention to the formula and what you're doing. Okay, so let's jump into an example. We're going to find the first and second derivative with respect to x for the given parametric curve. And then as a follow-up, we're asked for which values of t is the curve concave upward. Okay, so here's our two parametric equations. To get started, I'm just going to compute dx dt and dy dt first. Okay, so dx dt, that's going to equal 3t squared minus 12, and dy dt is 2t. So to start off, if I want to compute dy dx, remember that's equal to dy dt over dx dt. So that's going to be 2t over 3t squared minus 12. That one's done. See, look how straightforward. Check, done. Now, second derivative time. Make sure you write out everything really methodically, that way you don't mess this part up, okay? So I'm going to write out what the formula tells me to do. I differentiate with respect to t the first derivative. What's the first derivative? With respect to x, it's 2t over 3t squared minus 12. And then I divide all of that by dx dt. Okay, So when you're finding the second derivative with respect to x, you take the first derivative, dy dx, differentiate it again with respect to t, and then divide that result by dx dt. All right, let's continue. So now in the numerator, if I'm going to take the derivative of all of this stuff with respect to t, I need to use the quotient rule. So here we go. We've got low d high, so that's going to be 3t squared minus 12. D high is 2 minus high 2t. D low is 6t over low low. Square the bottom, away you go. And then I have dx dt in the denominator, which is just another 3t squared minus 12. All right, nice. Now let's simplify this a little bit more. So I'm going to distribute and clean up the numerator. We've got, let's see, a 6t squared minus 24 minus 12t squared. And then, well, watch this. Here's another 3t squared minus 12, and I've got 2 of them there. So I'm just going to write this as 3t squared minus 12 cubed. All right? Very nice. Let's see. In the numerator, I can combine some like terms. So I have negative 6t squared minus 24 over 3t squared minus 12 cubed. And I can further simplify because I notice I can factor a bit more in the numerator and denominator. So I could take out that negative 6, and then I have t squared plus 4 in the numerator over, now check out what I'm going to do in the denominator. I can take a 3 out, and then I have t squared minus 4 left, but this is all cubed. So I'm going to distribute that exponent to both the 3 and the t squared minus 4. Did you see that? So slick. And now I can cancel out a factor of 3 from the numerator and denominator. So that's going to be a 2. That's just 3 squared. So at long last, our second derivative is negative 2 times t squared plus 4 over 9 times t squared minus 4 cubed. Voila. There's our second derivative. Okay, how we doing? Surviving okay? Now remember we were asked something else. They asked us for which values of t is the curve concave upward. So in case it's been a while since Calc 1, let me refresh your memory. The curve is concave upward when that second derivative with respect to x is positive. It's greater than 0. So what I want to know is when is negative 2 times t squared plus 4 over 9 times t squared minus 4 cubed, when is that greater than 0? You have to be so careful when solving rational inequalities. You don't solve them the same way you do rational equations, for example, okay? So you are not allowed to do things like clear out the fractions, multiply through by the denominator when there's variables in the denominator. That's a big no-no. If you need a refresher on how to solve rational or higher order inequalities, I'll link a video here, but I'll just kind of walk you through the process. So we're going to look at each of the factors in the second derivative and see how it controls the sign, all right? Meaning, negative 2, that's a constant, so that's always negative, all right? Now I'm looking at t squared plus 4, the next factor. It doesn't matter what I plug in for t squared plus 4 is always going to be positive. So what does that tell me? That tells me the numerator of the second derivative is always negative, right? Because I've got a negative times a positive. Now let's look at what's going on downstairs in the denominator. This 9, this is always positive. And then look at, we have t squared minus 4 cubed. So that's really the only factor, right? Or the only term in the second derivative that could change from positive to negative. And if I want the whole second derivative to be positive, then what I need is for t squared minus 4 to be negative in order for the second derivative with respect to x to be positive. So this, let me write this out here. T squared minus 4 cubed needs to be negative, right? So if it's negative, then that would mean the denominator is negative, the numerator is negative, so the second derivative would be positive. Okay, that means I can ignore the other three factors or parts of the second derivative. All I need to focus in on right now to answer the question is, where is t squared minus 4 cubed less than 0? And that's the same as just figuring out where t squared minus 4 is less than 0, correct? Because if I cube it and it's negative, it's going to stay negative. Well, a couple ways you can solve this. This is a quadratic inequality. Sometimes I'll have my students factor. Okay, so t plus 2 times t minus 2. And then you make a number line listing the zeros of the quadratic expression. So this is a number line for t. I'm going to put negative 2 and 2 here. Okay, and a couple options. So here's one way you can do it. So t squared minus 4, if you were to graph it, that would be a parabola opening upwards, and the x-intercepts would be at negative 2 and 2. So the shape goes like this. So I know that that expression is positive on this interval, negative in the middle, positive over here. Another way without thinking of the graph of the parabola is just to use test values. So from negative infinity to negative 2, you could test with t equals negative 3. And you could test it in here or the factored form. And you could see, oh, you would get a positive value. And then here you could test maybe with 0 and then test with 3, either way, okay? Bottom line, I know that this expression is going to be negative on this interval here from negative 2 to 2. So that means t squared minus 4 is negative there. And as a result, the second derivative will be positive there. So I can finally give my answer and say the curve is concave upward for t between negative 2 and 2. Okay, very good. Now let's move on. Of course, we want to integrate these parametric curves, right? Why not? So let's talk about areas. If you have x and y parametric equations with parameter t, and f of alpha equals a, and f of beta equals b, where alpha and beta are the limits on your parameter t, okay? Then if you're integrating along the x-axis, the area is equal to the definite integral from a to b of y dx. And then you're going to end up actually evaluating this whole integral in terms of t with respect to t. So then you would have t equals alpha to t equals beta as your limits of integration. Y, I'm going to replace y with g of t. And then dx, look at dx. What would dx be? Well, since x is f of t, dx is f prime of t dt, right? X is f of t, which means dx dt is f prime of t, so dx is f prime of t dt. That's where that comes from. Boom. Let me highlight it for you. Okay, so that's the formula we're going to use. Let me box it. This is for integrating along the x-axis. Now, it does change a wee bit if we integrate along the y-axis. So you would still have x and y as functions of t. This time you have g of gamma equals c and g of delta equals d, where the limits on t, the parameter, are from gamma to delta. So if we're integrating along the y-axis, now we have the area equals the definite integral from c to d. They just switch, so you have x and then dy. And then similarly, you would have your integral from t equals gamma to t equals delta. I'm going to replace x with f of t, and then dy gets replaced with g prime of t dt. So here's the other formula. Okay. Good. And the curve has to be traversed exactly once. So if the curve like retraces over itself, then this formula will not give you the accurate area. It'll typically overestimate it. Okay, are you ready for some examples? I just got a couple for you, don't worry. Example 2, find the area under one arch of the cycloid. And we're given x, which is equal to r times theta minus sine theta, and y, which equals r times 1 minus cosine theta, theta between 0 and 2 pi. So to figure out whether or not we're going to integrate with respect to along the x-axis or the y-axis, we need to know what the graph looks like for a cycloid. So I'll draw that for you. It's depending on who taught you polar graphs and stuff, you may already be familiar with it or you may not. Okay, in this case, r is left in the equation. We're not given a specific value for r. So I'll just leave this. I'll label this 2 pi r. This is 0. And so the cycloid's graph looks like this. Something like that. And we want the area under one arch only. So that's all I'm graphing. So based on the graph, it makes more sense to integrate along the x-axis. So then I'm going to choose my formula accordingly. So I'm going to have area equals integral from theta equals 0 to theta equals 2 pi. And remember, when we integrate along the x-axis, I have y dx. A to b. That's the formula that we're using. So now substituting in everything for my parameter so that it's all in terms of theta instead, y is equal to r times 1 minus cosine theta. And then I need dx. So let's figure out what dx is. So this is y. And then now let's find dx. So since x is equal to r times theta minus sine theta, dx is going to equal, now r is just a constant, okay? So leave it alone. Leave him alone. Now we're differentiating with respect to theta over here. So I'm going to have 1 minus cosine theta and then d theta. So that's dx. I'm going to plug that in right here. So I've got r times 1 minus cosine theta d theta. This is my dx. Good? Okay, so now the question is how to integrate this thing. Let's drop it down here. First things first, I like to take those constants out of the integral so they get out of my way. Remember, r is a constant. I'm integrating with respect to theta. So I'm pulling it outside. So we've got r squared. Everything's already in terms of theta, so I'm just going to drop writing that, 0 to 2 pi. And then you have 1 minus cosine theta squared, correct? Yes, so this is going to be 1 minus 2 cosine theta plus cosine squared theta d theta. Ooh, let's see if you remember how to integrate this from so long ago in the semester. So 1, I can anti-differentiate that. 2 cosine theta, not a problem. What do we do with this cosine squared theta? Correct, we're going to replace it with 1/2 times 1 plus cosine 2 theta. Very nice. So now let's move on. We've got r squared, integral from 0 to 2 pi. Now look at this. I've got 1 plus 1/2, so that's 3/2, minus 2 cosine theta plus 1/2 cosine 2 theta d theta. All right, now it's time to anti-differentiate. Let's go. So leave that r squared out there. Then we have 3/2 theta. Antiderivative of -2 cosine theta, that's going to be -2 sine theta. And then antiderivative of 1/2 cosine 2 theta is going to be positive 1/4 sine 2 theta, right? Don't forget to divide by that 2 from 0 to 2 pi. Oh my goodness, we're doing so well. So now it's time to plug in those limits of integration. We've got r squared times 3/2 times 2 pi minus sine of 2 pi, that's just 0, plus 1/4 times, again, sine of 2 times 2 pi, that's sine of 4 pi, 0 again, minus, let's make sure, if I put 0 in for the lower limit, yep, everything is 0. So all that I'm left with is 3 pi times r squared. Wow, wow, wow. Okay, so that's the end of the problem. Yes, you do need to remember all the integration techniques that we went over at the beginning of the course, especially as you move on to Calc 3. They just keep popping up, okay? Wonderful. Now, let's practice one with the y-axis, right? Why not? So find the area enclosed by the following parametric curves and the y-axis. And here I wasn't given any limits on my parameter. I mean, naturally there's some domain restrictions, right? Because I notice y is equal to the square root of t. So t has to be greater than or equal to 0. I'm not allowed to plug in any negative values for my parameter. But besides that, let's make a table so we can see what this curve looks like, trace it out, and then we'll decide how we want to integrate it, how we want to set it up, okay? So this is kind of like a flashback to that first lesson that we just did recently, t, x, and y. And of course, I'm going to start with 0 for t, and then just fill in enough till I feel comfortable that I know what the curve looks like, especially with relationship to the y-axis. So let's do 0, 1/2, 1, 2, 3. Let's see. Oh, that was enough. I guess I felt like that was enough earlier. Okay. Fabulous. Okay, so if t is 0, both x and y are 0. If t is 1/2, x is going to be -3/4. And then I'm just going to approximate this, so y is about 0.7. If t is 1, x is -1, y is 1. If t is 2, x is 0, and y is rad 2, which is about 1.4. And then if t is 3, x is 3, and y is rad 3, which is about 1.7. Okay, so I already have a good idea what's going on. I know it already hit back to the y-axis right here, because x is 0. So in here is the loop that it makes with the y-axis. You'll see. Let's graph it right now. That's enough. That was certainly enough. So here's the y-axis. X goes between -1 and 3. All right. -1, 1, 2, 3. Beautiful. Y-axis, 1, 2, 3. Okay, so the curve starts at 0, 0 with t equaling 0. Then we go to x is -3/4, y is 0.7. So maybe somewhere around here. And then we have x is -1, y is 1. Then we have x is 0 and y is rad 2, which is about 1.4. So here's what's going on with the curve. Okay, this point happens when t equals 2. This initial point here is when t equals 0. Then when x is 3, y is 1.7, and it keeps going. But what we're interested in is the area enclosed by the curves and the y-axis. So we're interested in just this area right here. Okay, so that area is determined when t is bounded between 0 and 2. Okay, so that's going to help me out with my limits of integration. All right, very good. Now let's go ahead and set up our integral for the area. So what we're going to do is we're going to integrate along the y-axis this time. So area is going to equal the integral from t equals 0 to t equals 2 of x dy this time. All right, well, x I'm going to replace with t squared minus 2t, but dy I need to find first. So remember, if y, I'll do that over here, y is equal to rad t, then that means dy is equal to 1 over 2 rad t dt. Okay, or if you like using, this is t to the 1/2, then this is 1/2 t to the negative 1/2 dt. All right, so let's go back to the integral, replace everything so it's all in terms of t. So now I don't need to write t equals because everything's going to be matchy-matchy. So we've got 0 to 2. Now let's be careful here with this x dy business, because x is giving us the height, right, for the area. We're integrating along the y-axis. So I'm going to draw like a typical height here. So think of this as the height portion. And it's determined between x equals 0 and the curve here x equals t squared minus 2t. And so since it's bounded between those two, I'm going to have to take the right minus the left, or basically 0 minus t squared minus 2t. We didn't have to worry about that in the last problem because the curve went above the x-axis, so you subtracted 0, but you didn't really notice it. But since this one's to the left of the y-axis, we have to make sure we remember to subtract the 2. And then that's x, that's all of my x. And then dy, we have it over here. I'll write it as 1/2 t to the negative 1/2 dt. So that's my dy. Okay, good. So now let's just clean up and distribute. What do I want to do? Let's take this 1/2 out. Then we have integral from 0 to 2. I'm going to have negative. If we distribute, I need to add the exponents. So t to the negative 1/2, I'm going to add it to t squared. So then that's going to be t to the 3/2. And then this is going to be plus, because I'm also distributing this negative. Don't forget, 2t times t to the negative 1/2, that's going to be 2t to the positive 1/2 dt. Okay, and then now this is not such a crazy problem. So now we have 1/2. We can go ahead and anti-differentiate. So negative t to the 3/2, it's going to become t to the 5/2. So I need a 2/5 in the front, t to the 5/2 plus 2t to the 1/2, that's going to become t to the 3/2, and I need to multiply by 2/3. So we've got 4/3 t to the 3/2, and then evaluate this from 0 to 2. So this is going to be, I'll distribute the 1/2 at the same time as well. Let's get this ball rolling, you know. We've got here negative 1/5, 2 to the 5/2, plus 2/3 times 2 to the 3/2 minus 0. Now let's see, 2 to the 5/2, think. That's the square root of 2 raised to the 5th power. So 4 of them gives you a 4, and then you've got that 1 left over. So this is going to be negative 4 rad 2 over 5 plus, and then very similar. So 2 to the 3/2, that's the square root of 2 cubed. So that's going to be 2 rad 2 times another 2. You've got 4 rad 2, and then this is all over 3. Okay, and then if we get a common denominator, it's going to be 15. So if I multiply this by 3, I'll have negative 12 rad 2 plus a 20 rad 2. So our final answer is 8 rad 2 over 15. Okay, yay for radicals. Good. How are we doing? Okay, I think the next couple ideas are a little bit easier. So what's up next is arc length. So if you'll recall, we've studied arc length already for functions of x, right? If y equals f of x. And we found the arc length to be the integral from a to b of the square root, hopefully you remember this, of 1 plus dy dx, or f prime of x squared dx. Well, let's replace dy dx with how we know it's defined for parametric curves. And I'm also going to switch my limits of integration. So we're going to have t equals alpha to t equals beta square root of 1 plus, and remember we found, or we defined dy dx early on in the lesson. It's dy dt divided by dx dt. And then this whole thing is squared. And then similarly, I'm going to replace dx with dx dt dt. Okay, now if I take this dx dt and distribute it inside the radical, it's going to become squared, right? So then now I'm going to have the integral from t equals alpha to t equals beta square root dx dt squared plus, and then now it's going to cancel, right? With that dx dt squared in the denominator for the derivative. So all I'll be left with is dy dt squared and a dt. So that's actually your arc length formula for parametric curves. Isn't it nice? I always liked it a good deal. And this will come back if you have to take multivariable calculus. So don't forget it. Good. And then similarly, here's everything written out as a nice theorem. So the curve C is described by our parametric equations. You have to make sure f prime and g prime are continuous. Otherwise, dx dt and dy dt won't be well defined when you're trying to integrate them, and you'll run into big problems. And the curve has to be traversed exactly once, meaning you can't like retrace yourself because then the arc length will not be accurate. And then we have the length there, okay? Good. So example 4, all we're asked to do is set up an integral that represents the length of the curve. What's this little x doing here? Go away. Good. So x equals 1 plus e to the t, y equals t squared, and t is between -3 and 3. So let's just set up the formula. Arc length equals the definite integral from -3 to 3. And then I'm going to have the square root of dx dt squared plus dy dt squared dt. So let's go ahead, compute dx dt and dy dt. Dx dt is just e to the t, and dy dt is 2t. Oh, not bad. So this is going to be the definite integral from -3 to 3. We have square root of e to the t squared plus dy dt is 2t squared dt. And then let's just clean that up a smidge more. So we have the integral from -3 to 3 square root. This is e to the 2t plus 4t squared dt. Voila. And oh my goodness, you guys, do you realize we're asked to only set it up because we couldn't integrate this? How sad. All right, last idea, last example. Good job. Surface area. So the surface area of the curve given by the parametric equations, x equals f of t, y equals g of t, t bounded between alpha and beta, where f prime and g prime are continuous, rotated about v. First, let's look at the x-axis. We looked at this lesson already for surface area when we just had a curve defined as either a function of x or y, not parametric curves. And I showed how it's we slice cones and make these little bands to approximate it. If you forgot the idea, I'll link the video here, but I'm just gonna assume we don't need like a full-blown discussion all over again. So surface area equals definite integral from alpha to beta. We have 2 pi. If we're spinning around the x-axis, this is y. Okay, that's the radius. Watch the video again if you need a reminder why. And then the rest of it is the arc length portion of the formula. So this is the same, dx dt squared plus dy dt squared dt. T between alpha and beta. You end up, when you actually integrate, right, everything's with respect to t. So you replace this y with g of t. G of t. Bam. If you're spinning around the y-axis, what changes? Do you remember? Let me color code. X-axis, this is a y. If you're spinning around the y-axis, now you have alpha to beta, 2 pi x, yes, yes, yes. Y-axis, the radius is x. And then we have the same arc length portion. So dx dt squared plus dy dt squared dt. And yes, I would end up replacing x with f of t. Good? Okay, so let's just do one example. Find the exact area of the surface obtained by rotating the given curve about the x-axis. So I know I'm using 2 pi y for this case. So we've got x and y. And let's go ahead, let's compute dx dt and dy dt just so we have everything ready to go. So dx dt is going to be 3 minus 3t squared. And then dy dt is 6t. Okay, cool. So surface area is going to be definite integral from 0 to 1. Those are the limits on t. And then I have 2 pi y. What's y? 3t squared. And then the rest of it is the arc length. So then I have square root of dx dt squared. So 3 minus 3t squared squared plus 6t squared dt. Okay, now we just have to clean this up massively. So we've got integral from 0 to 1. I can take out a 6 pi, can't I? Let's do it. Go away 6 pi. I feel better already. T squared. Now let's multiply everything out under here. So we have 9 minus, this is going to be 18t squared plus 9t to the 4th plus 36t squared dt. And if you'll remember, these usually, everything under the radical cleans up in a convenient way. Someone sits down and doctors these problems so that they do. So 6 pi integral 0 to 1 t squared square root, what's going on under here? So we've got a 9t to the 4th plus an 18t squared plus a 9 after combining like terms. Well, I noticed I could factor out a 9, and then I have t to the 4th plus 2t squared plus 1. Conveniently, that's a perfect square trinomial. How fabulous for us. So moving on, we've got 6 pi integral 0 to 1 t squared times the square root of 9 times t squared plus 1 squared dt. Do you see that? Oh, from here on out, it's smooth sailing. We can breathe a sigh of relief. So when I take the square root here, I don't have to worry about any absolute value. T squared plus 1's never negative. So then we have here, this is going to be a 3, right? With my 6 pi, that means I've got an 18 pi out here. 0 to 1. And then I have t squared times t squared plus 1. It's not squared anymore. I took the square root. Very lovely. So then we have 18 pi times the integral from 0 to 1 of t to the 4th plus t squared dt. Oh, and then now it's just a relaxing polynomial. We could anti-differentiate this in our sleep. So we've got 18 pi times 1/5 t to the 5th plus 1/3 t cubed from 0 to 1 0 to 1 are some nice limits too. 18 pi, this is going to be 1/5 plus 1/3 minus 0. So 1/5 plus 1/3, if I get a common denominator, it's 15. So that's going to be 8 over 15. So we've got 18 pi times 8 over 15. Cancel, cancel. I can take out a 3, right? So this is going to be 5. This is 6. They wanted an exact answer. That's what we're going to give them. 48 pi over 5. Bam. So nice. Are you proud of this? This is a lovely problem, I think. So that concludes the lesson. I hope you enjoyed it. Don't forget to give it a thumbs up, subscribe if you haven't already, share it with your classmates. I would really appreciate it. And then stay tuned. We're going to dive into polar next and all sorts of good stuff.